Well, I'll bet some other people will join us as we get started. And looking at the clock, I hate to start late when people arrive on time. So I'm just going to say thanks for joining Seattle Friends of Fission to hear Jim Conca talk about nuclear waste. So we're a grassroots organization that brings speakers to the public to talk about the importance of nuclear power and its value fighting climate change and dispelling myths and misinformation about nuclear power. That's kind of our favorite thing to do. And Dr. Conca is a scientist in earth and environmental science, specializing in geologic disposal of nuclear waste, energy-related research, and at one time in his life, he worked for NASA on issues of exploration in space, I guess would be a simple way to put it. And he writes a weekly column for Forbes.com, which they're always great. He writes on energy and the environment and lots, not just nuclear, but a whole range of topics. So Jim, it's all yours.
Great, thank you. I'm actually gonna do the share screen. Is that all right, Carl? So that you can get me.
Go right ahead.
Oops, I'm disabled.
Oh. Very sorry. There we go. You're a co-host now.
Excellent. All right. There we go. And then we will put that up here.
Carl, can you mute us? Because for some reason I'm not muting. Sorry, folks. I'm being a little disorganized.
Good. That's all I want. Good. The reason I put this up here is that I want, as Paula said, I write for Forbes now, which is kind of crazy. I mean, as a scientist, it's pretty funny. In fact, I just got sent a press pass. It's like, what press? I'm a scientist. What is this? This is nonsense. But when I talk about nuclear waste here, I will discuss one of the sites that is in New Mexico where we have a nuclear waste disposal facility and no one even knows about, deep geologic underground repository. And in 2011, I took a Forbes editor downhole, half mile below the earth, and talked about, we were looking at nuclear waste already disposed in the ground. It's a piece of cake. It's very easy, actually. And he goes, oh my God, you want to write for Forbes? And I went, huh? I don't even have a Twitter account. He said, you will. So I do. And it's a different way of talking about science, of course. And it got me kind of off my duffer in the old scientific sense of being boring and talking about, scientific technical issues and blah, blah, blah. You really just want the whole story, and you want the perspective that has a lot of science in it, but is not only science. Okay, so there's a lot of other issues that intersect with nuclear and nuclear waste, history, economics, politics. I mean, it underlies everything. So if you want to look at the stuff I write about, talk about, just Google Conca Forbes and whatever subject. So nuclear waste, nuclear power, natural gas. I talk about all the energy issues because they're all interrelated. You really can't talk about one without understanding the other. So that's why I put this up there. So the big question tonight is, what's happened to our nuclear waste disposal program? It was on track. Now it's not. Why? What happened? As you might imagine, politics happened. Okay, so I need to get to that later. Okay, first we need a nuclear primer. Okay, a short primer. So everyone's up to speed on what I'm talking about when I'm talking about nuclear. I'm talking about fission and nuclear waste of different types. So uranium-235 splits easily. It fissions easily. Uranium-238 does not split easily. Uranium comes in a rock, just like iron ore. It's uranium ore, okay? It is naturally 0.7% 235 and 99.3% 238. There's almost no 235 left on Earth, okay? It was all the elements in front of you, your computer, most of your body, the walls, everything except hydrogen and helium was formed 6.3 million years ago in a nearby supernova event that blew all the heavies into our condensing solar nebula. So everything was all the elements on Earth were created about 6.3 billion years ago, especially the uranium. Now, the half-life of uranium-235 is 700 million years, which sounds like a long time, and it is. But 6.3 billion, it's been through 9 half-lives, so most of it is gone. On the other hand, 238 half-life is 4 billion years, so it's only been through 1 half-life. So most of uranium left on Earth is 238. Now, to have a controlled or an uncontrolled chain reaction, you need to enrich that in general, up to like 4%, 5%, depends on the reactor design. But it's still, even enriched up to that, it's still mostly 238. So what you do with uranium to enrich it is you mine the ore, you dissolve it up in acid, and you precipitate out what's called yellow cake, which is U3O8. And then you dissolve that up and put it through a bunch of spinning centrifuges. You turn it into a gas, uranium hexafluoride gas, and you put it down 30,000 super centrifuges, and 238, a little bit heavier, goes to the outside. 235, a little bit lighter, goes to the inside, and you just cascade over and over about 30,000 centrifuges until you enrich it to what you want. So again, if you want power in a reactor, you only enrich to 4 to 5%. It's fairly easy. If you want a bomb, it has to be all 235. It has to all split at the same moment, or your bomb will be a dud. So it has to all be enriched to greater than 93%. Right. That's why you can't make a weapon out of spent fuel from a nuclear reactor, because there's hardly any 235 in it, and there's hardly any plutonium in it. So when you want a bomb, it has to be all 235 or all plutonium 239. That's why it's difficult to make a bomb. Now, if you're a nuclear weapon, let me back up a little bit. When a neutron comes in and sees a 235, it hits it, and it splits the nucleus into 2 unequal pieces called fission products, and 3 neutrons come out plus a bunch of energy. Okay, so 3 for 1 in general. 1 neutron in, 3 out. Sometimes it's 2, sometimes it's 3. So that's what does it. 3 for 1, such a deal. That's why this works. Now, if you're a bomb, you're all 235, so those 3 neutrons generally see another 235, and they split. And then you're at 9, and then 2781, boom. Okay, so in a microsecond, you're at 10 to the 20 splits, 10 to the 20 neutrons, and that's your bomb, because the power from a bomb has nothing to do with radiation. It has to do with these 2 pieces flying apart at high speed. Okay, and if you have 10 to the 20 of these flying apart at high speed in a microsecond, you're going to generate quite a bit of heat and pressure, and that's your blast. It's a big bomb. A nuclear bomb has nothing to do with the radiation. A little bit of radiation that comes out at the edges, the little burst at the edges, is trivial compared to the power of the bomb. It's a big bomb. So we talk about Hiroshima and Nagasaki, which were about 13,000 tons TNT equivalent. So, a 13 kiloton equivalent nuclear weapon. They mean if you could put 13,000 tons of TNT in one spot and ignite it in 1 microsecond, you couldn't tell the difference between that and a nuclear weapon. You get the same mushroom cloud, you get the same blast, you get the same kill, except at the edges, you wouldn't have a little burst of high energy neutrons and gamma at the edge that goes just beyond the blast zone. But, so a bomb is a bomb, nothing to do with power. Now, if you want power, or if you want to make plutonium for a bomb as well, it's not all 235 or plutonium 239. It's, again, 4 or 5% uranium 235. And when the 235 nucleus splits into 2 pieces and you get 3 neutrons out, they generally do not see another 235. They generally see a 238, because it's almost all 238, right? It's 96%, uranium 238. And that doesn't split. It captures that neutron and then quickly double beta decays to form plutonium 239. It's breeding plutonium 239. Now, there are little side reactions that are not as important or not as numerous as this, and they produce other things like neptunium and americium and other things like that. But the main one is plutonium. So you are breeding plutonium from the uranium 238, okay? Now, plutonium, of course, burns even better. Plutonium-239 burns even better than uranium-235. And as soon as it's formed, it starts burning. So it doesn't build up to any amount. It's not you start burning it. Now, if in a commercial reactor, you leave the fuel in for about 6 years, okay? And so most of the 235 and the plutonium-239 that's been bred is burned up to produce power, okay? It's still mostly 238. Now, if you want a bomb, you have to be very careful because you can't leave the fuel in the reactor more than 6 months, okay? So right away, if someone like Iran or North Korea or something is putting fuel in to a reactor and taking it out in 6 months, then you know they want a bomb. Okay, it's very clear. There's no fooling someone about whether you're making a weapon or not. We know who's making weapons and who's not. So if you take it out of the reactor after 6 months, because if you leave it in for more than 6 months, you'll start breeding in neutron poisons that will make it impossible to make a bomb, like plutonium-240 and plutonium-242. They don't split, they absorb neutrons, and the whole thing fizzles out. So again, bomb making is interesting. We can have a whole talk on that, but it has nothing to do with commercial fuel. You cannot make a bomb out of commercial fuel. It's a special way to make bombs. And that's what we did at Hanford, a long time ago. Now, what this tells you here from the rest of the slide here, is that you have 2 types of waste. Okay, you have the fission products formed from splitting uranium-235 and plutonium-239, these pieces, okay? And then some of them are strontium-90, some of them are cesium-137. There's a whole slew of fission products that when combined, about equal the weight, 235, the mass of uranium-235. So you get all these pieces. Now, those pieces are the ones that are sometimes very hot. So nuclear fuel is made hot. When we talk about hot fuel that you don't want to be standing next to, they're talking about the fission products like strontium-90 and cesium-137. That's why we have them in fuel pools for 5 years after they come out of the reactor. So they stay in the reactor 6 years. You take them out, put them in a fuel pool till almost all of the fission products decay away, except 2, strontium-90 and cesium-137, right? They have a half-life of 30 years. So the rule of thumb is, 7 half-lives to background. So for somewhere over 200 years, you have strontium-90 and cesium-137, which give off gamma, and you have to shield it. So that's the hot stuff, short-lived, very short-lived, hot. Then you have the long-lived stuff that isn't very hot. So you have the stuff that's been formed by neutron capture, like neptunium and plutonium. Now, uranium and plutonium, you can hold them in your hand. They're not very radioactive. They have a long half-life. And the longer the half-life, it means it's not very radioactive. The shorter the half-life, the more radioactive, because it's really, zipping, throwing off subatomic particles and energy, and it's gone quickly. So a short half-life means it's very active. So it's very radioactive. Long half-life means it's not very radioactive. So I could actually hold plutonium in my hand, and it wouldn't hurt me. You have to powder it and breathe it in for it to do any harm. Okay, so you probably haven't heard that kind of thing, okay? There's 2 types of nuclear waste formed in a nuclear reactor: the hot, short-lived stuff, and the long-lived, not very hot stuff. So keep that in mind when you're thinking about nuclear waste and nuclear repositories, those 2 types of general types of waste. Let's see. So in America, we have 4 categories of nuclear waste, and I'll go over them. Spent nuclear fuel, which is in the news all the time. So it is, a fuel bundle. It's solid. It's metal and ceramic, and there's no liquid there. Now this is in a reactor, in a fuel pool, but it's solid. It's not liquid. Can't leak like the gunky stuff at Hanford. So it's a solid, it's a reactor fuel rod. So when we talk about spent nuclear fuel, that's what we're talking about. Then there's the next 2 categories: high-level waste and transuranic waste, are both bomb waste, only bomb waste. All right. So high level waste only refers to bomb waste, and transuranic only refers to bomb waste. So if you hear someone talking about a commercial reactor having high level waste, they're wrong. There's no high level waste at a commercial reactor. There's only spent nuclear fuel. So when we talk about high level waste, then we're talking about bomb waste, and we're talking about Hanford site. Okay, so we have lots of bomb waste there, and I'm sitting right next to the Hanford site. So we have these tanks, and it's kind of this peanut butter gunk. You know, it's not very nice. It's not solid. Okay, it's gunky. Okay, that's what makes it difficult to handle. And then transuranic waste, and I'll talk about where these two come from, is a whole bunch of different stuff. It's contaminated mainly with plutonium and americium, but it could be concrete, it could be sludge, it could be old lab equipment that's highly contaminated with plutonium. It's just a bunch of junk, and you put it in drums and waste boxes, and that's transuranic waste. Then we have low-level waste, which is mainly soil and a bunch of other stuff. Okay, so it's kind of weird. Low-level waste doesn't require deep geologic repository, but the top three do. So spent nuclear fuel, high-level waste, and transuranic waste all require deep geologic disposal by law. Right? Now, Washington State has all four of these wastes. So, hey, congratulations to us. We have more waste than almost anyone else because of Hanford. Okay, so we have a lot of high-level waste, a lot of transuranic waste. We have a lot of low-level waste. We don't have a lot of spent nuclear fuel because we only have one nuclear reactor right here next to me. It's not at Hanford. People think this nuclear reactor, the Columbia Generating Station, is at Hanford. It's not at Hanford. Okay, it's not on the Hanford site at all. All right, but it's next to it, so people get confused. But it is a commercial nuclear reactor here. Now, so to tell you where high-level waste and transuranic waste are, and this is kind of important. In fact, it's very important. Where these come from. So if you're making a bomb, like I mentioned, you put it into a weapons reactor, not a commercial reactor, a weapons reactor, like we have out here at Hanford, the 9 we had, from beginning in 1943, 1945, out to about 1983 is when we were making plutonium for bombs, right? So what you do is you would put the fuel into the reactor, the weapons reactor, for 6 months, take it out, take it apart, dissolve it up, all right, and put it through a series of steps that would concentrate the plutonium into a pit that you then make into your bomb. Okay, so there's 5 different processes for this, and that's what determines the waste. So the first 2, okay, you dissolve up the whole fuel bundle, and you're trying to separate uranium and plutonium, and all the junk, like the fission products and everything else, and the lead and all the other junk, goes into the first set of tanks. By definition, they're high-level waste. Nothing to do with the level of radiation. This is really key. Nothing to do with the level of radiation. It's just that they came out of these 2 steps. And these 2 steps is where you take out most of the cesium and strontium, which are the heavy gamma emitters. So we just put those in high-level waste tanks. And there's 177 of them. Then the next steps are polishing steps to remove and concentrate the plutonium and also the uranium, which you can then put back through the whole process. So anything coming out of these 3 steps go into the transuranic tanks, the true tanks. And we have about 20 of those here at Hanford. In fact, most of the ones that are leaking at Hanford are true tanks. Okay, they're not high-level waste tanks, they're true tanks. All right, which is, they leak a little bit, but we'll talk about that too. So again, high-level waste come out of the first 2 steps. Transuranic waste comes out of the polishing steps. So high-level waste has all the gamma emitters, and transuranic waste has all the alpha emitters. Right? So there's 2 types of waste. Now, a funny thing has happened since 1970. We removed most of the cesium and strontium from these high-level waste tanks, and the rest has been through at least 1 decay life, if not 2. Right? So they're not high-level waste anymore. Okay, that needs to sink in. Okay, there is no high-level waste left at Hanford, except the barcode still says high-level. All right, because they came out of these 2 steps. but we took out all the hot stuff, or it's been decayed away, and they're not very hot anymore. In fact, most of the stuff left in the high-level waste tank would meet the criteria for the definition of true or low-level waste. So here we are at Hanford with 177 tanks that used to be high-level waste, and they're not high-level waste anymore. So what do you think that means? Should we care? Should we just keep treating them like a high-level waste, even though they're not high-level waste anymore? Because it's a lot more expensive to treat it like high-level waste if it's not. We have ways to get rid of true and low-level waste, and we'll talk about that. And it's a lot cheaper because it's not high-level waste anymore. So this is now the dynamic at Hanford. And it's very important because most of the people in Washington State have no clue that there's no high-level waste left at Hanford. They all think it's high-level waste because it's called high-level waste, not because it is. It's because it's called high-level waste. So it's one of these weird administrative, bureaucratic nonsense things that is going to end up costing us about $200 billion extra. I'm not sure if you care whether it's going to cost $200 billion extra just because the definition is wrong or not, but something you should think about since we're broke as a nation. So it kind of matters. All right, now, there are three ways that science enters the decision-making process in our society. Number one, it is completely ignored. Okay, now I don't feel bad anymore. I'm used to this. Okay, I've worked on projects for years. I mean, I've worked on some projects for like 10 years before I got the answer. And then to have it ignored is kind of depressing. But again, I'm used to it. Now, this sounds a lot worse than it is, because most decisions that we make in society don't really need to be based on science. I mean, okay, you can ignore the science and it's no big deal. Okay, but some things do. Okay, and that's important to know. Number two, it actually enters in before the decision is made. Wow, this is what you want. All right. This is why we have the greatest scientific community in the world in history of the planet, is so we can have science-based decisions when we need to. So you go to a bunch of scientists and you say, okay, I need this answer. You can take a few years to figure it out, but let me know what it is. Then we tell you, and you can either ignore it or you can use it to make your decision. So number one is not so good. Number two is what you want. But then there's a third one. And the third one is science enters after the decision is made. And this is called a science-supported decision, which it turns out is most of our science decisions are science-supported, meaning you've made a decision to do something based on politics, economics, history, geography, whatever reason you have chosen to make the decision. You make this decision, and then you look at the scientists and you say, make it happen. Now that's happened to me a dozen times in the last 30 years. Okay. It's interesting. It's like, really? You made the decision already and you don't even know what the science is going to tell you, but okay, I get it. Now what's important is that, NASA, right? The Apollo program, that was the number three. We went to the moon, not at all based on science. We went to the moon based on military and political issues, not science. So we decided to go to the moon. And then we looked at the scientists and engineers and said, can we do this? And they said, yeah, we can do this. And we did it. Great, wonderful. But don't think it was a science-based decision. It was a science-supported decision. Now, our nuclear waste program started out as two. Okay. In 1957, it was a science-based decision, what we would do with our nuclear waste. It was a brilliant decision. It was great. Scientists were involved, scientists like me, geochemists. Where should we put this nuclear waste and how should we do it? Then it became three in the 1970s. And that's where all the problems began. And that's why we're in a mess. And that's why Hanford is not cleaned up. And that's why Yucca Mountain is not going, because it started out as a two and it became a three. So let's go back to when it was a two. So in 1957, we had made a fair number of bombs, and we had just fired up the first nuclear reactor at Shippingport. okay, the first commercial nuclear reactor. And so now the predecessor to DOE and NRC, Department of Energy and Nuclear Regulatory Commission, the predecessor was the Atomic Energy Commission, all right? And it's split in the 70s into two pieces, DOE and NRC. But it used to all be one. It was Atomic Energy Commission. And they went to the National Academy of Sciences in 1955 and said, we're building up some of this weird waste. It's kind of weird. We don't have much of it. We never will have much of it, but it's really bizarre. Could you tell us what to do with it? And so National Academy of Sciences did a very nice study, took about 2 years, 1957, came out with their report. And they said, deep geologic disposal, okay? The Earth is the only thing that can actually handle this stuff for 1 million years, okay? Now, I love the pyramids. They're great, love them, but humans do not make things that last 1 million years, okay? And if you're going to depend on something that humans made to contain something that's still going to be around in 1 million years, then you're off the mark, okay? So you want to find a geologic formation because the Earth makes rocks that last billions of years, okay? So you want to find the right rock and you want to put it there. That's it. Very simple. We know that. We've known that for 60 years. And so the best rock, it turns out, is salt, massive salt. And in fact, I have a piece right here. It's a massive piece of salt, okay? It's tight. It takes water 1 million years to move an inch in this rock because at a half-mile depth, it creeps closed. Under pressure, it cannot sustain a fracture or a pore space or an opening. And that's what you want. You want something that is not only good to contain your nuclear waste, but something that will fix itself if something happens.
Jim, show us that salt again for just a moment.
Good. So this is major salt. Now, this geologically, as a geologist, this is called a soft rock because it's you can drill it easily and you can squeeze it and all that kind of stuff. But if I threw this at your head, it would really hurt because it's very heavy. But it's a soft rock. It's not a granite. It's not a hard rock. And because it's a soft rock, under pressure, it creeps closed. That's what you want. You want it to creep closed. You don't want it to maintain openings where water can get through and your waste can get through. So this is why this was a hands down easy decision. It probably took a bunch of geologists a lunchtime, okay, to pick out this rock because we all know this is the best rock. And the best salt is in the Permian Basin of New Mexico and Texas, and the Delaware subbasin, particularly near Carlsbad, is perfect for this. That's where I got this piece from, because we have a deep geologic nuclear repository there that no one knows about, or very few people know about. It's in the right place. It's in the right rock. So that's the decision. 1957, we're going to put this in the Delaware subbasin in Permian salt. We'll just find the excellent, the perfect spot. At first, AEC went to Lyons, Kansas, and tried to use an old salt mine, which was dumb. You don't use an old salt mine. Salt mine was meant to make money. Okay, it wasn't meant to dispose of nuclear waste. So you start out, you don't need an old salt mine. You don't need something old. You start out new in a fresh place, and that's Carlsbad. So we eventually ended up in the Delaware subbasement of the Permian Salt Basin. Now, that was 1957. We did this, done. It was a science-based decision, number 2. Then 1970s came around. The AEC established these 4 categories of nuclear waste that I mentioned. Before that, it was like all of this was going to go in one place, which it should have, but all of this was going to go in one place. Now we're going to split it all up into different types. So we're going to split it into these 4 categories of nuclear waste. Then EPA was formed, and 1976, we outlawed commercial reprocessing of spent fuel. That was later reversed under Reagan, but no one remembers that. They just remember it's against the law to reprocess, which is not anymore. But we don't want it. We don't need to do that anyway. And then this is the weird part. This is where it gets weird and political. Is that someone had, Jim Schlesinger, the first Secretary of Energy, had his ear and said, we're not going to reprocess, but we might change our minds. So why don't we have a retrievable repository? Yeah, that makes sense. That's kind of like a screen door in a submarine. No, it doesn't make sense, because you don't throw out something that you want to be gone for 1 billion years and then decide, well, you might get it out later. I mean, that's dumb, okay? You throw out something you don't want to get out later. And it doesn't matter. You wouldn't want to get this out later. It's waste. It really is. Okay, so, but then, this idea that, oh no, we gotta now have 2 repositories or 3 repositories. So one is going to be for spent nuclear fuel and high level waste, and that has to be retrievable. So the salt is out because the salt creeps closed. Okay, you're not going to get anything out of that. It creeps closed rather fast, which is great, what you want. But we want to retrieve this maybe. And so we need a separate site. Okay, well, that number one, that started the downward slide. Okay, now unbeknownst to most people, because transuranic is not what anyone understands or knows or has ever heard about, so that still was good to go into the salt. Okay, so out of these 4 categories, we have a transuranic waste repository in salt, just where we said we should put everything, and that's in Carlsbad, and I will talk about that. So Nuclear Policy Act came about as a result of all this in 1982, and that's what I'll talk about. Now, what I have these graphs down here for is this is the way it was in 1970, right? Now, transuranic actually has 2 parts, the remote contact RC waste, remote handle waste, and contact handle waste. So remote handle waste is really hot. So it's kind of like high level waste in the level of activity. Contact handle waste is not very hot. That's all the alpha emitters. So, sorry, let me get back here. So since 1970, what's happened is that most of the high level waste is gone. It all became transuranic or low level. So things have changed from 1970 to 2018. To present day, yet our handling of it has not changed. Our definitions have not changed. Nothing has changed with the reality that the tanks have changed. So let's chew on that for a bit. So 1982 comes around, Nuclear Waste Policy Act. 17 candidate sites were chosen for 2 high-level commercial waste sites. So not just 1, but suddenly we need to have 2 high-level waste sites. One's going to be in the east and the north, and one's going to be in the south and the west. And that was another weird thing that some non-scientists came up with, that we need to spread the risk around as though that's going to reduce the risk. No, when you spread something around, you increase the risk. We only need 1 repository. We don't have enough waste for 2 repositories, and that would be dumb to have 2 repositories. So you only need 1, it's not that much waste, and you put it in the best rock. So anyway, they came up with 17 candidate sites. Then, come 1987, those had been whittled down to 3 candidate sites for the high level and spent nuclear fuel repository. One was Yucca Mountain, Nevada. You've all heard of that probably. That's the one that was eventually chosen. Hanford, Washington, so right outside my window here, Hanford, Washington, and Deaf Smith County, Texas. Now, who was Speaker of the House in 1987? Anyone remember? Jim Wright from Texas. Okay, so Texas is out. Who was House Majority Leader? Tom Foley from Hanford, from Washington. And there was this new junior named Harry Reid from Nevada. And all they did was say, Harry, it's yours. That's it. That was it. That was the decision. And it was a totally political decision. It had nothing to do with science. Then, and I was there at the time when they picked this, I was actually working on Yucca Mountain beginning in 85. So 87 rolls around, and I'm at Lawrence Livermore, and we're all gathered together, and we're told that it's Yucca Mountain. And we look at each other and go, Yucca Mountain? Well, that's a crappy place. Why did they pick that one? Well, they picked that one because Harry Reid had no power then. Okay. Now, the funny thing, of course, is that he became Speaker of the House. So what goes around comes around. And you have to worry about that kind of thing. So fast forward to 2008, Harry Reid's majority leader, Barack Obama, just was elected president, and Reed told Obama, if you want my help in the Senate, you're going to kill Yucca Mountain, which he'd been trying to kill forever anyway. And he did, which was fine because it was a lousy place. So Yucca Mountain was halted, and Obama put together this Blue Ribbon Commission to develop a new strategy. And that's where we are today. Of course, everyone has ignored the recommendations of the Blue Ribbon Commission, as you'd expect. And that's where we are now. Yucca Mountain was picked, and we did all this work on it. It was great work. Really proud of it. I'm one of the license application authors of the license application for Yucca Mountain to the NRC. Very proud of it, but it's a lousy place. So, what does make a good deep geologic nuclear repository? And you should kind of want to know this, right? There are 7 criteria we have used for the last 50 years to decide this. One, you need a simple hydrogeology. All right, it's got to be simple. You can't have, it's so complicated, you have no idea where the water is or where it's going. All right, because you have to predict whether this is going to work far into the future. So it needs to be simple hydrogeology. It needs to have a simple geologic history. Okay, it can't be so complicated that you can't tell what's going on and what's going to go on, because it's so complicated you can't figure out anything out. So it has to be a simple geologic history. It has to be a tectonically interpretable area. Now that's a funny term. You need to know where the faults are. You need to know what's moving, what plate boundary issues you've got, whether everything's being uplifted or down sunk, or whether volcanoes are going to come in and rip the place apart. So you need to understand the tectonics of the area, which is fine. You need minimal reliance on engineered barriers. Like I mentioned, the pyramids are great, but you don't want to have to rely on human-made things to make this work. You want to pick the rock that you don't need any of that. All right, that's the whole point. You need to have a performance that's independent of the canister. Okay, the canister should just be for transporting the waste to the site. You shouldn't depend on the canister to last 10,000 years or 100,000 years. I mean, again, you're back to this idea that you do not want to depend on human-made things, human engineering, to protect this waste, to isolate it from the environment for 10,000, 100,000 million years. Okay, you want a rock to do that. And then this last one is kind of funny. A geographic region that has existing and sufficient social, political, and economic infrastructure that you can carry out the operations without being near a metropolis. Okay, we call this the Walmart effect. Okay, if there is not a Walmart within an hour's drive, you don't put it there. Okay, because no one will move there. Okay, because if you have a Walmart, that means you have schools, it means you have hospitals, it means you have churches. You need society. These people that are going to work at this site have to be able to go home at night, and they should not drive more than an hour. So this is kind of an interesting thing. It turns out this is probably the most important part of these rules. And so it's kind of funny. So these are the 7 criteria, and we'll go over that. So based on these, let's look at Yucca Mountain. Now, Yucca Mountain is a highly fractured, oxidizing, variably saturated, dual porosity hydrologic system that sits on the edge of the Las Vegas shear zone. Now, what words in that paragraph make you feel good about Yucca Mountain? Okay, it is a lousy site. I'm sorry, it's just a lousy site. And as a geologist, and I worked on this for 25 years, trying to make, because I'm an engineered barrier guy, so trying to make the site work. And yeah, if you sink 500 billion extra dollars into this, you might be able to convince yourself that you can engineer around the fact that you picked the wrong rock. Okay, okay, fine. Okay, but it's a lousy rock. So in fact, going over this list of criteria here, nope, doesn't have a simple hydrogeology. It's very complicated, actually. It's interesting because the work we did at Yucca Mountain gave us the tools, the modeling, the computer modeling capabilities to model the subsurface. It's really amazing what we can do now because of Yucca Mountain, because Yucca Mountain was so complicated. Then simple geologic history. No, it's in the, it's not, okay? Because the reason we call it the Las Vegas shear zone is because the Mojave desert, the Mojave block, the plate, tectonic piece that holds the Mojave, is rotating along the San Andreas Fault on the south and the Garlock Fault on the north. And so the whole thing is twisting, and it goes right through Vegas. It goes kind of right through Yucca Mountain. Okay, so this is not what you want. Okay, but I will give it to you. Yeah, we know what's going on tectonically. It's horrible, but we know it. So okay, I'll give that a yes. No isolation robustly assured, not for any type of waste. So now we need to vitrify the Hanford waste because we're putting it in a lousy rock. That's the only reason we're vitrifying the Hanford waste. Okay, it's dumb. It's a dumb, very, very bad thing to do, to vitrify the Hanford waste. Chemically, it doesn't like to be in glass, but we're doing that only because Yucca Mountain's a lousy rock. Okay, so this, 1987 really put us on a bad path. No, we are heavily reliant on engineered barriers. Okay, Yucca Mountain could not go if it doesn't have 7 engineered barriers. Okay, no, the canister has to be super copper canister with ceramic. It's absurd. Okay, but I'll give it to you. It satisfies the Walmart effect. Pahrump is about an hour away, so that's where everyone would live, unless they wanted to drive all the way to Vegas. So, as a result, to fully implement Yucca Mountain, which was only supposed to cost $30 billion in the beginning, is going to cost well over, now it's up to $500 billion to put it at Yucca Mountain, and it probably will keep going up. Now, to put the repository in the correct rock, salt, in the Delaware subbasin would only cost about $30 billion. So what is the problem here? We're not made of money. Nevada doesn't want it because it was a political decision. We know where to put it. So this should all be done. We should have been doing this for years and years. Now, so here's the extreme engineering with all these engineered barriers to make Yucca Mountain work. Now, it turns out we already have a site that meets all the 7 criteria. You don't need anything. Okay, the rock does everything it's supposed to do, and it can handle any type of waste, including high-level waste, and spent nuclear fuel, and transuranic. And it's called WIPP, the Waste Isolation Pilot Project. And it's at the Waste Isolation Pilot Plant in southeast New Mexico, about an hour's drive from Carlsbad. So that's the Walmart effect there. Now, because no one actually knows, the public doesn't know what transuranic waste is, never heard of it before, it kind of quietly went into the salt as we planned, okay? But it was only permitted and licensed for transuranic waste, even though it was designed and built in between 1979 and 1983 for all nuclear waste of any sort. So again, we chose this correctly via science, and we were ready to go, and then all the rules changed, politically, and only transuranic was allowed to go here, which is fine. Now, 16 square miles was set aside in 1992 to put WIPP there, to put nuclear waste in this rock. 16 square miles. You don't need anywhere near that, but 16 was set aside out of 10,000 square miles. So there's 10,000 square miles of this rock where we want it. So there's plenty of room. But the 16 square miles is all we need for the next 1,000 years. Now, WIPP is ahead of schedule and under budget. Now, what federal program is ahead of schedule and under budget? Please tell me. And that's because it's the right rock. Now, Yucca Mountain is 20 years over schedule, beyond schedule, and is 10 times over budget because it's the wrong rock. Okay, so the rock actually matters. As a geologist, believe me, the rock matters. Now here's WIPP. This is the surface facility. There are 4 shafts into the underground, a half mile below the surface. And there's all these horizontal tunnels that are called drifts. And then there's all these panels. This is all mining terminology. So panels, and then each room, there's 7 rooms in each panel. And each room is a football field in length and 30 feet wide and 13 feet high. Okay. So it holds about 12,000 55-gallon drum equivalents of nuclear waste, but whatever container you can get to it can go down into it. Now, we actually have filled almost 7 of these panels. Okay, we're beginning to fill panel 8, and we're going to put in a couple other panels. So again, this has been going great guns. Now there was one, I can't call it a leak because WIPP performed as it was supposed to in 2014. Someone at Los Alamos put wrong stuff in the drum, and the top burst open underground, and it contaminated panel 7, a part of panel 7, and everyone freaked out and all that, but nothing actually happened. No one was contaminated. Nothing really got out. The equivalent of 100 smoke detectors got out, but nothing happened. So that's the only thing that's happened in 1999, 22 years. This has been operating brilliantly because it's the right rock. Now, why is this rock there? Well, during the Permian, which was from about 270 to 225 million years, the Proto-Pacific Ocean was off the coast of Utah and Arizona. There was a little arm of the Proto-Pacific that was coming into Texas and West Texas and South New Mexico, and that little arm kept getting shut off from the ocean, probably by tectonic activity, earthquake and mountain building. So it would get shut off, and then it would evaporate. The whole basin would evaporate, and then it would fill up again, and then evaporate, flood, evaporate, flood, evaporate for 60 million years. And it laid down 6,000 feet of salt. And the top 2,000 feet, called the Salado Formation, is ideal for this. That's what this piece of salt comes from. So it's pure salt. I mean, I actually grind this up and make margarita salt out of it. It's really kind of fun. It gets the conversation going too. Now I took that out before the waste went in, so that's okay. But yeah, so this is ideal. Now, what's even more is if you look close in that salt, you'll see little square bubbles. So as the ocean was evaporating, the salt was crystallizing, and it crystallographically trapped 225 million year old seawater, right? And in their square bubbles, it's kind of fun. So these are all, they're just about the size of a grain of sand or so. I mean, they're very small, but you can see them with the naked eye if you hold the piece of salt up to the light. Now, in my old lab down in Carlsbad, we separated, we took out that seawater, and lo and behold, we found DNA in it, and bacterial husks, halophilic bacteria, and cellulosics from cell walls. This is the oldest DNA ever found. And it's a testament that this is the perfect rock to put nuclear waste, because nothing's happened to it. Now, biomolecules generally do not last 200 million years. They're gone pretty fast because either the rock is exposed at the surface to cosmic rays and solar radiation, so it's radiolytically destroyed, or most rocks actually have uranium. I mean, there's uranium in the wall behind me. There's uranium in the floor that you're sitting on or standing on. There's uranium everywhere. Enough of it that it would radiolytically destroy biomolecules if it sits around in them a long time. But this is pure salt. There's no uranium in this salt, no potassium 40 in the salt. So it's pure salt. And it was never buried deep enough to get hotter than 41 degrees C, which is the thermal denaturing point for biomolecules like proteins and DNA. So nothing's happened. I mean, there's no volcanism, no faulting, no folding. Nothing has happened to this rock in 200 million years, and nothing's going to in the next 200 million years. You could not find a better rock than this to put nuclear waste in. It's also, like I mentioned, it's a soft rock geologically, so there's no blasting. So you just have these are called Marriott continuous miners. They're these big carbon tungsten fingers that just kind of dig out the salt. It's great. No one gets hurt doing this. You don't have to blast or anything like that. And so this is cutting out one of those rooms. It's a football field long. It's only 30 feet wide and 13 feet tall, but that's where you put this waste. And beginning in 2007, we started shipping the really hot stuff there. So this is a 72B cask, transport cask that you would be putting any high-level waste, spent fuel, or the transuranic waste we put in it, this is how you transport this around the country. We do this all the time. There's never been a problem with nuclear waste shipment around the country. And we have gone on millions of miles with pretty hot stuff. We know how to, this thing is impermeable. I mean, we drop this, off of cliffs. We submerge it in water for days. We put it in jet fuel fires. I mean, we run it into a brick wall at 80 miles an hour. It just bounces around. It's really quite indestructible. So transportation is not an issue. People think it is, but it's not. So here's what it looks like down a half mile below the earth in WIPP. This is, let's see. This is panel 5, room 4. So here's this guy. He's a rad tech, and he's taking measurements of radiation. He's getting almost nothing. So here's the waste, and it's in different containers. These are standard waste boxes from Los Alamos. This is a seven drum. We call it a 7-pack. It's shrink wrapped, 7 55-gallon drums together, and then there's a 10 drum overpack. So again, this is how you transport the waste. Now this is called contact handled waste. It's mainly alpha emitters. Now, alpha radiation won't go through your dead skin. So all you need is a 1/4-inch mild steel, and it's good to go. The hot stuff behind him is in the wall, and that is robotically dug out, a 14-foot hole. You robotically put in your waste, and then you robotically put in a 4-foot metal wrapped cement plug, right? And that's in all the walls. So you put the hot stuff in the walls, and then you backfill the entire room with the contact handle waste. It's quite brilliant and quite easy. So here's this guy standing there in front of nuclear waste, even the hot stuff, and he's getting 1/10 of the radiation that we're all getting sitting here listening to me talk. All right? Because he's a half mile below the earth, so cosmic rays and solar rays are pretty much filtered out. Not all of them, but most of them. This is pure salt, so there's no uranium or potassium-40 or radon or anything else here. It's easy to shield this stuff. So he's getting 1/10 of the radiation that we're getting. And he's standing in front of nuclear waste. Right? This is easy. This is really, really easy. And when I used to take down senators and other people down there, they'd come up and go, "My God, this is great. Why aren't we doing this?" And I'd say, "Well, that's your job. Okay? Our job is to make this. Your job is to fill it, or to pass laws that allow it to be filled." So again, I'm sorry I didn't upgrade this. It's been going for 22 years now, and there's just been no problem. So once you fill the room, it begins to close. So in 10 years, the roof and the walls and the ceiling and the floors all come in and start crushing this down. And in a while, it's just crushed back to what it is. So the reason this works so well, this is nature's trash compactor. Okay, it's really great. There's no question about this. And so once it's back to what it was, crushed down, these, excuse me for getting a little wonky here, technically wonky, but this is the permeability. So the hydraulic conductivity, how well water flows through this rock. And that's a low number. Okay, 10 to the minus 14 meters per second. It takes water and any contaminants in it 1 billion years to move an inch, and that's an upper limit. It's actually 0. It's actually molecularly tight. And the diffusion coefficient is even less. Now, that's because the properties of the rock. Now, not to get weird about this, but it's almost no water, and it's all in those little crystallographically trapped bubbles, and a little bit of crystal lattice water. The pH is perfect, so that things don't move. The EH, the reducing nature of this water is incredibly good. It's the most reducing groundwater in the country, and you want that. Because when you're reducing versus oxidizing, so, when you oxidize, when you're in contact with oxygen in the air, like Yucca Mountain groundwater is, it tends to make everything move. So plutonium moves when it's oxidizing. It doesn't move when it's reducing. Technetium moves when it's oxidizing. It doesn't move when it's reducing. So you want reducing groundwater, and this is the best there is in the country. The thermal conductivity, how fast the rock conducts heat away so the whole thing cools off quicker. It's 5 times better than crystalline rock like Yucca Mountain. Okay, so you can load up you can load the heat 5 times as you can in any other rock, which is great. And then the weird thing is that the annealing, or this creep closure of the salt, how fast it creeps closed and closes off all fractures and pore space and everything else, goes with at least the 6th power of the temperature. So the hotter the temperature, the faster this closes, the better it works. So this is not what you would think, right? That the really hot waste, which you think is going to be difficult to handle, works better in this rock because it closes quicker. I mean, there just is not a rock you could manufacture that would do this job better. Now, the period of performance that this rock gives you without trying is 200 million years. At Yucca Mountain, we had to struggle for 10,000 years. We had to prove that the Yucca Mountain Repository, with all our engineered barriers, would actually work for 10,000 years. That was not obvious, okay? But this does, you get 200 million years without even trying. So because of this, if you put it in the right rock, you don't need any engineered barriers, although EPA requires one. So we have one at WIPP just because we need to, by law. The waste form is irrelevant. It doesn't matter whether it's solid or concrete or sludge or anything else. So it doesn't matter what it is because the rock handles everything. Now, in order to get it on the road, Department of Transportation requires that there's no free liquid. So it has to be dry. So that's why we talk about grouting or vitrification or heating it up and drying it out, whatever. There can be no water or no liquid in the waste if it's to get on the road. So that's fine. You don't need to have a canister that's worth anything. It can all fall apart the first year after it's in the ground. There's no adverse temperature effects, and the fluid inclusion migration is irrelevant. So there really is nothing you can point to in this rock that fails. In fact, EPA requires a failure scenario, so we had to make up one because there's no natural failure scenario to this rock. And the one we made up was kind of funny. It's like someone was watching old Road Warrior movies. This far into the future, when people can't make cement anymore, but they're drilling for oil at 10,000 feet and they drill into this repository. Even that doesn't fail. Okay, you have to Swiss cheese it with holes and then hit a theoretical brine pocket at 10,000 feet. And then that has to come up through your repository and move through the repository and up an old well because you don't know how to make cement anymore, but you're still drilling to 10,000 feet. Okay, whatever. So, but even that doesn't fail. So even if you make up stuff, this doesn't fail. Now, here is the 16 square mile satellite image footprint, and the subsurface structures is on top of it. So the footprint, the final footprint of WIPP will only be about a square mile when its present mission is done. All right, out of 16, it'll only be about a square mile. So again, 10 years ahead of schedule, $1 billion under budget. That's great. Now, if you say, okay, well, what happens if we decide to expand it? Well, okay, so we put all the high-level waste and all the true waste in Hanford and Savannah River and everywhere else. Hanford has the most. And okay, so you double it to 2 square miles. Okay, and if you put all the spent nuclear fuel there, you would not even add another square mile. So there's plenty of room here. It's the best rock, plenty of room. We know how to do this. We've been doing it for 20 years. It's hard to think of putting it anywhere else because you won't. No one will accept it. So the fact that WIPP exists, that it's been working, that we've been disposing of pretty hot stuff there already, and there's been no problems, and it's the right rock, it's really hard to think that you're going to convince South Dakota to take this waste. So that's where we're at. So now there's plenty of salt in the country. But the best stuff is this Delaware subbasin around WIPP. I mean, the other salts are okay. They're at different depths. They're different types. But if you require another place, okay, we can find another place. But you don't need more than one place. Now, Texas also wants waste control specialist in Andrews, Texas, wants to put the repository there and wants to put an interim storage facility there because they have a lot of the same salt. But it doesn't matter where you put it in here. Now, back up now. So transuranic waste, the second category of bomb waste, has been being disposed of in WIPP in New Mexico for the last 22 years. But for spent nuclear fuel, we put it in dry cask storage. So I don't know if you've heard of dry cask storage. After you take the fuel out of the reactor, you put it into pools of water for 4 or 5 years until most of the fission products are decayed away, except for strontium and cesium, strontium 90 and cesium 137. And then you take it out and you put it into these dry cask storage, which are massive cement and steel. They're even laser pinged in terms of their wells, so the wells can't corrode. It's really great. They're not very hot anymore. I mean, they're hot. You don't want to be next to the fuel unshielded, but it's this massive shielding, and it sits on a cement pad. You can fly an airplane into this. Wouldn't hurt them much. You just stand them back up. It's really quite easy. So it's these dry cask storage, a cement pad, and a fence and some guards, and that's it. It's the easiest thing you can do. Now it's different than high level waste because high level waste in the tanks at Hanford, no longer high level waste, but whatever you call it, is gunky peanut butter stuff, salt cake. It's nasty stuff. So you have to solidify it before you can ship it out anywhere. Now you've probably heard of deep borehole injection of nuclear waste, which is an interesting idea. It actually works. As a geologist, once you get something down this far in the crust, there is no natural process to get it back out anywhere near 1 million years. So yeah, if you can get it down there that far, it ain't coming out again. All right. Now, can you get it down that far? Now we've drilled holes much farther, much deeper than this, than 5 kilometers, but they're smaller holes, to get oil and gas. But we can do it now. So we can do this if you want. We can put it deep borehole. What's interesting about this is that it doesn't matter where you are in the country. If you do deep borehole, when you're this far in the crust, all states are the same. The entire country is the same. All right, it's deep in the basement rock. So all of the aquifers, all of the stuff that you care about is way up here, less than 1 kilometer depth. So you're way below that. So you can have a deep borehole disposal facility in every single state, right? If you have nuclear waste in your state, you just put a bunch of deep boreholes in there and you can dispose of it. Now that scares everyone in Congress because everyone in Congress has been saying for decades that we're going to get the waste out of your state and put it in one place. So this is a complete departure from the traditional strategy of finding a place, a single place to put nuclear waste. All right, but it is not a bad idea. So here we are. These are the only possible outcomes for our nuclear waste disposal program. This is it. There's no other alternatives. All right. So either the defense waste at Hanford and other DOE sites, transuranic and high-level waste, either you redefine it to what it is, because it's all true or low level, and you ship it to WIPP, like it should be, because if it's transuranic, it should go to WIPP. Okay, but no one likes that in New Mexico because everyone says, you lied to us. You said it was, only for true. But yeah, it is only for true. But the high-level waste is no longer high-level waste. It's transuranic now, so it should go to WIPP. So that's a weird political, societal thing you have to overcome. It's not technical. We know what it is now. Or if that doesn't work, you find a second salt repository because we know where the salt is, and salt is cheap, right? Because it's the right rock. Now, so that's the defense waste. Or if you don't do one of those two, then it stays right where it is. Okay? Which is likely what's going to happen here for the next 50 years, is all the nuclear waste is going to stay right where it is because no one can come up with an agreement. Okay? Because we're just a bunch of children now in this country. We can't actually make a national decision anymore. And so it's state against state. And it's like, and no one cares about science, so we're not going to make the decision. I mean, I'm being a little cynical there, but that's where we are. So it could be that all this waste stays right where it is, right? Now, then you have to look at the environmental impact statements of that, because we have environmental impact statements for the waste just staying at Hanford and never leaving the state. So that's defense waste. Then the commercial nuclear fuel is, right now, it's being put in dry cask storage. You either say, okay, it's going to go to a centralized interim storage facility, or it's going to stay right where it is at 32 different states, all with interim storage. Okay, so, okay, it's one thing. These dry casks are good for 150 years anyway, so it's not like you have to do anything quickly. And by that time, it'll be much cooler. So the commercial waste is actually easier to deal with than the defense waste because it's solid and it's in dry casks, and they're good. Now, Bill Gates and others who are designing new reactors, Bill Gates wants to build a fast reactor that will burn this waste. Okay? But even if you burn it all, again, you're still going to have some waste to deal with. But it's all going to be fission products, which are all short-lived. So now you only need a repository for 1,000 years instead of 1,000,000. And that could be in salt. Okay, whether it's at WIPP or next to WIPP or in another state that has salt, don't know. Or you could put it in deep borehole. So that's it. Either you expand WIPP, you have a second salt repository, or you put it deep borehole, or you just keep everything right where it is. Those are the only alternatives. And we can go Q&A to Q&A now, and we can say, is that true? Is that the only alternative? Yeah, it's pretty much the only alternative because we've exhausted them all, and no one wants this. No one wants to make a decision, even though nuclear waste is easy and safe. I mean, it's so bizarre. I've worked with it for almost 40 years now. Okay, it's no big deal. And I've dealt with chemical waste and biological waste, and that stuff is nasty. That will kill you, and it does kill people all the time. Nuclear waste has never killed a single person in the world, not even in the United States, but in the world. It's never killed anyone, nuclear waste, okay? It's not a reactor. This stuff in dry cask storage is just cooling off. There's no more nuclear reactions going on. It's not like a reactor that can melt down or anything. It's already cooling. So all you have to do is sit it there. So there's nothing easier or safer than interim storage of spent nuclear fuel, but you wouldn't know that by talking to most people in the public. And why would you? I mean, why does anyone think they can understand this stuff without actually being in this field? This is not intuitive. Oops. So, Paul and Carl, do you want to open up to Q&A?
Yeah, let's start with our friend Steve Verdi on Facebook asks, there are at least 2 nonprofits, one run by a state legislator, who claim to be really worried about the leaking tanks and groundwater contamination with high-level waste. So what should we say to them?
Well, actually, there isn't any danger. Okay, the leaking is no big deal. So I'm going to go back here to, okay, these are the tank farms. So these are the leaking tanks. Some of them are leaking, not all of them, but some tanks are leaking. They're leaking very slowly. It's no big deal. This tank waste poses no, and I mean this, no measurable risk to human health and the environment off-site. Off-site. All right. There's no mechanism, no geologic mechanism or any other that could get anything, any amount of radioactivity to anyone in Seattle or Portland or even Richland, just down the street, basically. Okay. There's no way you can get anything out of this geologically. I would have to go to one of these tanks, take a shovel pull, drive to Seattle, and throw it on your head. And that's about the only way you're going to get anything from these Hanford tanks. Okay, now the senator who said that or whatever, they obviously don't know fate and transport. They don't know how things move through the air, how they move through the water, how they move through the ground. Okay, this is my specialty. There are processes that move things around on the earth, and there are none that can get anything from these tanks out. Okay, there is none. Leaking, right. by the time it reaches the river, it's so dilute, the radioactivity is only about 4 millirem a year. Okay, now that's 1/10 of the background. So, you can be afraid all you want, but there is no risk to the public. Now, that said, the only risk is to the people that work with it, that are on site, all right? Because it's there. They're handling it. They're working with it, okay? So yeah, there is a risk there. And in fact, if you vitrify this waste, the risk is greater. Okay? The risk to the workers is greater because vitrifying this stuff is not easy. It's dangerous and it's not easy. But it's no risk to the public, all right? In fact, the risk is so small. We've done all this. Our models are quite good. We've been doing this for 30 years. The risk is so small, you can't measure it. It is statistically not different than zero. All right. Now, scientists hate to say never, they hate to say zero, but this is statistically not different than zero. All right. There is no measurable risk here. So you can get all upset if you want and gnashing of teeth and all that, but you're not going to get it. No one's going to be hurt by this waste unless you work with it. All right. If you work with it, you could get hurt, but that's only the workers on site, and no one has yet. So that's okay. I'm not sure if that answers the question, but yeah, everyone's upset about it going to Seattle. It's like, how do you think it's going to get to Seattle? It gets out to the river and it's gone.
Right.
There's enough of it to get to Seattle.
And I just have to remind everyone to think about where they were on May 2nd, 2019, when we had an NRC extraordinarily severe event at the Harborview Research Facility when they sliced open a cesium source. And no one seems to pay attention or have any concerns about that. The fire department swept it up. It's fine. It's handled. And to suppose we can do that with a cesium source, like a mini Goinia incident in Seattle, almost.
And then right. and you're worried about something 250 miles away.
Right.
See, I mean, distance makes a difference. It really does.
So we've got one question from Abraham, and that is, how is waste from uranium enrichment, the tails, how is it handled?
Okay, that's a good question. Uranium enrichment is mainly you're left over with uranium-238. Okay, so it's basically like ore. So it's like the original uranium ore, and it's not very radioactive. I mean, contrary to popular belief, I mean, I have a bunch of uranium here, actually. You can hold it in your hand. It's no big deal. It's only alpha. It won't go past your skin. I mean, again, you have to make it into a powder and breathe in a ton of it in order to do anything. And that's, that actually the uranium as a heavy metal like lead is probably worse in that case than the radiation. So again, it's not very radioactive. The half-life of 238 is 4 billion years. So it's just not very radioactive. And it's treated like low-level waste, which it is. It's low-level waste. So when I mentioned, let me get back here. Let me go through this. When I went back here and I talked about low-level waste, it's treated like low-level waste. So we have several low-level waste disposal sites, Clive in Utah, Barnstable. I can't remember the four, but in fact, U.S. Ecology out here in Hanford is a low-level disposal site. So we know how to deal with low-level waste, and mine tailings are low-level waste. Did that answer that?
Yeah.
Okay.
So John in the Zoom meeting has a few comments, I guess. About U-238 being disposed at.
Yes.
Yeah.
Okay. Okay. So they're stored also at different sites like Paducah and Portsmouth, but the ultimate disposition is going to be in low-level waste sites.
Mm-hmm.
Now, why do you say uranium-238 gets more radioactive? Are you talking about the radon that's produced from it, its daughters?
Yeah, decay products. There you go.
Yeah. But again, that's the same as the ore itself. And so uranium ore is not very radioactive, and we don't flip out like we do with nuclear waste from reactors. But so the daughter products are there. That's why everyone's so worried about radon, although there's never been any real serious threat from radon, but we pretend it's really bad. And that's okay. It's easy to deal with.
Yeah. So, we've got another from Chris Bergen on Facebook. Dr. Ben Franta has studied fossil fuel companies' denial of climate change. So this is a little off the rails, but I trust Chris. They hire smart people who understand much of the science and then mischaracterized. One of his references is a 1978 book, Regulation Game. Have fossil fuel interests aided in mischaracterizing nuclear waste and its regulations?
Yes, absolutely.
Wow.
Because nuclear power is the only thing that goes up against gas and coal. Seriously. Okay, they don't care about wind. I mean, in fact, the oil and gas industry supports wind like crazy because they know you need oil and gas if you're going to have a lot of wind. So T. Boone Pickens, if you remember him before he died, he was a real character. He was a gas man. But he was supporting wind because he knew that his gas would be called on to support the wind. So for every 4 megawatts of wind, you have to put in a megawatt of gas, or a megawatt of hydro, like we do up here. So we use, in the Pacific Northwest, we use hydroelectric to balance the deficiencies of wind. But yeah.
Very good. I'm always we're currently having a little fight about a petition and trying to get people to sign on to this. Some very serious scientists, and they're very, very gun shy about the idea of solidifying this statement that fossil fuel interests have kept nuclear down.
Oh, I also see from John, sorry, that WCS is not proposing using salt. Yeah, they're not proposing deep underground geologic repository yet. They're talking about interim storage and low-level waste disposal in the clay. Sorry, that's a shallower unit. But if they, they want the interim storage facility on there. But if they want to deal with the higher levels, spent nuclear fuel, high level waste, or transuranic waste, then they will go into the salt. And they've been talking about that too, but that's a step too far for them right now.
I'm going to read the question from John, different John out loud. Different. I have a 2-part question. 1, could you share anything that's known about how other countries, such as China or France, store their waste? Let's cover that.
Yes, very important, because no one, although Finland is now beginning, no one has a deep geologic repository for spent nuclear fuel. For one reason, they don't have much of it. So France, which is second only to the US in the number of nuclear power plants, they store all of their waste for the last 40 years in one building. It's like no big deal. All right. So, and they do a lot of reprocessing, and all that waste is still stored in one building. So again, the thing about nuclear waste to remember is that it's about 1 million times more energy dense than coal. All right. So the volume is nothing. Okay. So the idea that we would have more than one repository for our nuclear waste is also insane, because we don't have enough of it to warrant more than one repository. And so, most people just store it because it's no big deal, because there's not much of it. Okay. But Finland is going to start disposing of theirs, but they don't have much. Okay. Most, the nuclear countries that have most reactors are the United States, then France, then it used to be Japan, and then Korea and a few others. So now China is building more nuclear power plants than anyone in the world, and they will continue to that. They break ground pretty much every month on a new nuclear power plant, a big one. And they are planning 180 new big nukes by 2035, 180. Now, we only have 99 left, maybe 98 now, 97 as we keep closing foolishly, perfectly good ones. But so they are looking at the, what's the plateau? Oh, come on, the uplift in China. Jeez. Yeah, I'm sorry, I'm losing it here. But
I'd have to look.
Yeah, so they have a spot that they're looking at, which is fine. And no one has the salt we have, though. I mean, really, nothing is like WIPP. Germans tried to dispose of nuclear waste in one of their salt deposits. It was a crappy salt deposit, and it was thin. It was anticlinally folded and deformed. It's like, that's not a good salt. Ours is 2,000 feet thick, and nothing's happened to it in 200 million years. So that's what you want. You don't want something that's 60 feet thick or 100 feet thick. You want a massive salt deposit. Okay, and there's two parts to that.
Yeah, the uplift, was that Tibet?
Yeah, Tibet, right, the Tibetan
There you
plateau.
go.
Right.
The second part, suppose in the future we create many more nuclear reactors across the world. How do you anticipate storage of that waste with possibly few local suitable areas?
Well, again, we could, if we made nuclear 50% of our energy supply, WIPP could handle it all for 1,000 years. Okay, so there's just really not much problem there. And again, we're talking about such a small amount of waste. Now, we can just switch over to coal. Again, coal is about 1 million times the volume of waste. And we don't deal with that at all. I mean, we have coal impoundments just to sit there until they break and flood little villages and kill everyone. I mean, this is relatively common, which is insane. That even happens in the Appalachians here. Yeah. So, it's like, if we can't deal with our coal waste, then nuclear is great because it's such a small piece of that volume. So if we go to deep borehole injection, or we go to the salt deposits we have, I mean, again, it's just not that much waste.
And as long as human civilization survives, we're going to have these reactors. We're going to have reactors that need to be guarded and watched, and secured and monitored, and the waste can just sit right next to them, right?
Right. Now, Korea. Now, I noticed John says Korea's mine repository in granite, but that's not a high level or spent nuclear fuel repository. That's basically a low level, intermediate level site. So, and that's great. It's a good one. Now, he also mentioned that UAE, United Arab Emirates, has salt domes. Now, salt domes are okay. They're not as good as massive bedded salt, though, because salt domes, by definition, are doming. They're called, I'm losing my terminology here. Diapirs. They're called diapirs. So they're actually moving upwards, and so they're vertically fractured. So most salt domes are vertically fractured. So I wouldn't put it there, but it's not that bad. I mean, it's certainly better than Yucca Mountain.
And you spent some time in the UAE talking to folks about this kind of thing.
Yeah, right. Because of the Baraka reactors that have just fired up here.
Yeah. So I think the first one is on the grid, and the second one has begun criticality. So that's a very exciting prospect to see 2 of 4 nuclear reactors in the UAE with a non-enrichment agreement. Absolutely super exciting stuff. Yes. There's a few comments on Facebook now. Let me skip John for a moment, and we'll quickly cover Eugene's question. What does the U.S. Navy do with nuclear waste after refueling?
We store them up here at Hanford. So we store the whole. In fact, you take out the whole reactor, and like for aircraft carrier and subs, and you put the old reactors here in at Hanford in shallow burial. Now, whether they were originally supposed to go to Yucca Mountain, that's a tough one because they're big. But again, we can deal with that. Whether we have to chop them up or something, we'll have to do that too. But again, not that many of them. But that gets back to...
Yeah, go ahead.
Yeah, that gets back to the small modular reactor kind of things. The nuclear Navy is a treatise in how to do small modular reactors. That's what they are. And they've never had a problem. And no one ever gets hurt from the radiation. So it's like, we've done this, we know it. Unlike the popular press, I guess, or mythology, nuclear is no big deal. It's easy.
That reminds me, they're reactor parts with the fuel going to Hanford, but in the case of San Onofre, they recently took the reactor vessel and they put it somewhere in Utah, I think it is.
Yeah, because it's not that hot.
Mhm.
Again, it's not that hot. It's
So that's
probably
low level.
Yeah, so it's low level waste.
Okay. And our friend John Dobkin, who's in California now, says, what's the best path for the U.S. to solve long-term spent nuclear fuel disposal?
You want an interim storage, centralized interim storage like near WIPP, that you can put everything together, because again, there's not that much, and it's kind of ridiculous to have it spread out all over the country. Some places not in great places. So you pick a good site, and physiographically near WIPP, there's no one lives there. Within a 45-minute drive. It's in the middle of nowhere. It's inhospitable. Okay, it takes 600 acres to support one cow, so it's not like you're interfering with anything. And you sit it there until you decide how to dispose of it permanently. And it can sit there for 100 years because dry cask storage is really good and really simple. And the containers just last forever, especially in a desert like near WIPP. So or wherever else. So you find an interim storage facility and you store everything there until we get our act together and decide to have a deep geologic repository for our spent nuclear fuel as well as our high level waste. So whether you expand WIPP or you find a second salt repository, whatever, but you're not going to do it you're not going to solve it until you do that. And everyone gets all upset because they don't want it in their backyard. It's like, yeah, but someone has to, okay, you just can't keep shoving it off on someone else. If you have the best rock and the best place, it should go there. Okay.
And no one gets to ask where a gas plant or where a coal plant goes. They're just there. Right. They're just there. So John in our Zoom thinks that maybe we made an error. The naval reactors have been defueled, and a quick Google seems to indicate that the naval reactors facility at INL might be where the removed fuel goes.
I'm sorry. Good catch. Good catch, John.
Good. And let's see. Eugene on Facebook is asking, did the NRC just affirm that there's a no safe radiological dose? And what should we think of that?
That's the same old crap that we've been doing for 70 years. There is a safe dose. I mean, anything less than 10 rem is nothing. We've never had any health effects from 10 rem. Okay, yeah. Acute or chronic, it doesn't matter.
Yeah.
So, we knew well before the Cold War that safe doses below 20 rem per year were fine. Okay, we learned that from the radium dial girls. We learned that from minor accidents and medical stuff. We knew that. By 1943, we knew that. Then the Cold War started. And then, Hermann Mueller and a few others decided that they were going to ignore scientific data and just declare that there was no safe dose, that anything down to 1 photon is going to kill you or possibly kill you. And we call that the linear no threshold dose hypothesis, which is wrong. We know it's wrong. But it was incorporated into regulations around the world in 1959. And we have not been able to get it back out because everyone said, well, yeah, we kind of know it's not right, but it's conservative, right? It's like, no, it's not conservative. It's just wrong. Okay.
Right.
And the problem is when it scares everyone because you're actually telling everyone that there is no safe dose of radiation. So people don't want to get x-rays. They don't want to get MRIs. They don't want to get CT scans, which actually saves lives. Okay. Because they're so afraid. They don't want to eat potato chips because potato chips are the most radioactive food, right? You know that, right? Yeah, 13,000 picocuries per 12-ounce bag. Holy
That's a big number. Oh my goodness.
Yeah, what's a picocurie?
I don't know. But
anyway, yeah, so that's the most radioactive food, but you don't care about that. I mean, the fat and salt will kill you, not the rad. But,
right.
It's not intuitive. There's just no way. You have to know this stuff.
And I think I remember some of the discussions at, for instance, the CDC. I read over some of these where they said, you haven't given us a better model, but the existing model only exists because of the influence that was exerted over the Nobel Committee at that time.
Right, absolutely. And China and the Soviet Union at that time used the linear no threshold dose hypothesis to stop United States above ground nuclear tests. That was one of the big uses of this. One of the big reasons is if you think all radiation is bad, no matter what, then you better not be testing nuclear weapons above ground, right? I mean, it was a perfect, logical conclusion based on false logic, but that's okay.
It was a pretty good decision in the long term, because we see the amount of background radiation. We see spikes every time there's a huge forest fire in the Pacific Northwest. That's all from the 530 atomic weapons that were detonated in our atmosphere. We take something like Fukushima and Chernobyl, and those together added, I believe it was less than 5% of the total contamination, whereas like 90+% came from the atomic weapons, and so much more came from medical procedures. People just put it into the sewage, and it's okay. It gets carried away, and your municipal waste service takes care of it.
Right. So it just, the bottom line is it takes an awful lot of radiation to hurt you, period, to cause cancer. And we know that from the Japanese bomb survivors. None of the bomb survivors that got less than 20 rem showed any effects at all in life. No cancers, nothing. Okay, so that is a clear threshold right there, 20 rem. You can back it down if you want to 10 rem. But there are places on the earth that are 10 rem background, and people live there and they don't have any increased cancer rates or anything else. So what more do you need? I mean, this is straight epidemiological data. It's like, you find populations that live in different background radiation doses. You don't see any effect at all. And what people forget about the linear no threshold dose hypothesis is that it demands that there's a relationship. If you have one population that lives with a background of 0.6 rem and someone that lives in a background of 5 rem, there has to be a difference. There has to be a higher cancer rate, and there isn't. Okay, LNT demands there be a difference. It's not like, oh, well, something else is going on. Yes, something else is going on, because anything less than 10 rem is not harmful. So that's what's going on. So it's very difficult. It's very difficult to understand why we still have this nonsense, but besides it, it's just conservative. It's the way it's always been. But this fear actually kills people. So Fukushima, people should not have died. No one died from radiation, but they should not have died from fear, which they did. So 1,600 people died simply from being ripped out of critical care facilities, and we got to evacuate quickly because we might get 2 rem next year. It's like, what? You live in Colorado, you're going to get 2 rem. So it is important. It's unlikely to change anytime soon. It should, but it's actually quite important.
So our friend Chris Bergen has a bit of a wild and a little bit of morbid hypothesis. Fuel rods are hot both thermally and radiologically. If someone were to hug a fuel rod just as it's removed from a reactor, would the heat kill quicker than the radiation?
Very cute. That's funny. No, the radiation will kill you first.
Especially because the thermal load of these decays really rapidly. It's like below 3% after a few hours.
Yeah. I mean, once it's in the, that's why we keep in the pool for 5 years, because 99% of the heat is gone, because all the short-lived stuff is gone, and most of the fission products are really short-lived. I mean, hours, days, minutes. I mean, they're all over the board, but only cesium-137 and strontium-90 are more than a few years, and so that that's fine.
Does it take us 5 years to gather up enough spent fuel from our one reactor to fill a cask?
Oh no. It kind of, well, that's a good question. Damn.
It might, because I saw the regulation is 1 year, and I know that even San Onofre had a variance where they were able to offload immediately.
Ah, okay. I don't know that. I should know that. I apologize, but yeah.
Eugene is a great space travel fan, and he'd like to know, as far as you understand it, because you're a geologist, not a medical expert. Right. What do you think of eventual human Mars missions with respect to the radiation dose?
I want to go. In fact, Mars was, when I was at NASA, Mars was one of my planets. Yes, that's why you want a nuclear rocket. Now, NASA is actually developing a nuclear rocket, an actual nuclear rocket, because it'll get you there like 5 times faster. So the total dose will be less. We have come up with anti-radiation suits called smart suits that you wear, that you actually protects you from most rad. But there's, you're going to get a dose. It looks like it may be even up to like 10 rem a year, which, during the trip. So if you're only there, well, if you're on the trip, if you're a nuclear rocket, you can get there in 6 months. If you're a chemical rocket, it's going to take you a few years. But so that's why you want a nuclear rocket. When you land there, of course, you can set up shielding. You can be underground, stuff like that.
Yeah. In fact, that reminds me that there is such a thing as the Nuclear Thermal Propulsion Program at our good friends at Ultrasafe Nuclear Company. And so I put that in the Zoom chat, and I'm trying to put that in the other chat. Let me refresh this. And you can go see what they're doing with respect to, and you're still sharing, by the way, Jim.
Yes.
With respect to nuclear thermal rockets, as well on the channel here. We're broadcasting on the Seattle Friends of Fission channel, so not on this channel, but on my channel, yestv.org. You can see the presentation that one of the people from USNC gave us on on rockets. Eugene has a witticism. What should we call Mars geology?
I do. What's the punchline?
Yeah. I think it's a punchline. Geo. It's not geo. It's Marsology. No.
Anyway, I put up this figure here to show you the yield in fission products, the mass number. So cesium and strontium are only one of many different fission products that, when you add them together, equal about uranium 235, equal about 235. So strontium 90, cesium 137. That's, you add those together and you're 230. Actually, that's 227, but they don't come out the same. They don't come out at the same time. So you have a low. There are 2 different sizes. You have a small piece and a large piece. Most of them are actually not very radioactive. Some are very radioactive, but strontium and cesium are the only 2 that matter because their half-lives are 30 years. Mm-hmm.
I saw before I had to reload the chat, and sorry if I missed a question or 2. I did have to reload my chat app. But John Dobkin made a comment that the fuel that came out of the Songs facility there put out less energy than a hairdryer, so about 1,500 watts.
Yeah, it's not really that hot. Okay, I mean, it builds up if it's contained, but it's just not that hot.
Abraham asks, can you use spent fuel, or I suppose, are there isotopes in spent fuel that you can use as a neutron source?
Oh. I don't think californium is made. I don't know. That's a good question. If there is, it's not much, not many. That's why you have to have a neutron trigger to get the reactor going.
Good questions. Eugene suggests Aresology instead of geology.
That's good. In fact, when you think about Hanford and the contamination, the rad never caused anyone to have cancer at Hanford. I mean, not at Hanford. What was the bad thing was beryllium, right? Beryllium and asbestos and lead and a few other heavy metal contamination. But beryllium, the reason we use beryllium, I don't know if you know this, but it is to produce neutrons to trigger the atomic bomb. That's why you use beryllium. You make a beryllium foil, you impregnate it with americium-241, which is alpha, and when alpha hits a low Z nucleus like beryllium or lithium, it produces a ton of neutrons. Okay, and so when the gun type, Hiroshima gun type hit itself, there was a beryllium foil impregnated with uranium-241, and that was your neutron trigger. You needed enough neutrons to get it going so that it would all fission in a microsecond. So
really good. We got a few more come up. Is France's small amount of waste due to reprocessing? Do they use MOX fuel?
yes, it's not. They don't reprocess that much. That's kind of a misunderstanding. They reprocess some, just like Japan reprocesses some, and England reprocesses some, and they produce a MOX fuel, mixed oxide fuel of plutonium and uranium. But most of it is simply spent fuel that's sitting there.
Wow!
There's two different storage facilities. One is for spent fuel, and the other is for reprocessed waste. And I think Hague is the reprocessed waste.
Yeah, I think you're right, because it's very small and they're all in drums right there underneath the floor.
Right.
Yeah. It's really, really striking. It's one of the most striking things that I've seen about, waste storage.
Right.
It's amazing.
But I am not a reprocessing advocate, okay? Because uranium is too cheap and too easy. There's too much of it on Earth. And so the idea of going through the reprocessing process, it has its own issues, and people get all excited about that or upset about that. So you don't need it. You don't need it, especially since we're going to become. We know how to extract uranium from seawater now, specifically just uranium, and so then there's a limitless supply, and so we'll never, it'll be as renewable as the wind. Yeah,
4 billion years, literally.
Yeah.
We will not run out at the current rate of consumption until after the sun has burned out. And that's astonishing.
Even 10 times the present consumption. You don't have to worry about uranium supplies.
Right. I think we're near the end, so I just want to let everyone know we have one thing that we'd like to get everyone interested in, and that is the Senate Bill 5244 in Washington State. Now, what this is a bill that we're trying to educate our legislators on. This opens up more incentives for nuclear startup companies to produce advanced reactors in Washington State. This gives, as you know, Washington State has a gross receipts tax and an O&M tax on their net income. And so that's difficult for a startup company to get involved in Washington State. And so it's our customary practice that we give new startups a tax holiday. Wouldn't it be great to give a fusion research company in Western Washington a tax holiday? Wouldn't it be great to give a fission advanced reactor company a tax holiday on those O&M taxes? So again, that's Senate Bill 5244. And we really encourage you to look into this bill, talk to your legislator about it, find out what they think, come back and talk to us about it. We'd love to start organizing support, especially from Democratic state senators and state representatives. We'd love to hear exactly what's going on and how we can support legislation like this to bring more clean energy to Washington State.
Nice. Excellent.
Oh, I spy one more. Let's make this the last one. Chris Bergen asks, Rosatom will build reactors outside Russia and take back the used fuel. What do they do with it?
You don't want to know.
Oh, no.
No, I mean, again, they're just storing it. It's a brilliant marketing ploy, though. And we should do it as well, because I'd rather we supply nuclear technology to the world than Russia. But yeah, so they've said, if you only have 1 or 2 reactors in your country, you don't need $1 billion disposal program. So Russia, like us, has more nuclear waste than almost everyone else. And so, they said, take our reactor, we'll take back the waste. Such a deal. Okay. We should do that too, but we don't.
Very nice. So I think we're running low on questions, and it's been an hour and 45 minutes. Thank you so much for your time Jim.
You're welcome.
Let's give everyone a chance to go camera up after I cut the stream. So I'm going to go ahead and say goodbye to Twitch, Facebook, DLive, FC2, Trovo, just broadcasting everywhere, just to talk to as many people as possible, and get this information out there. So we'll say goodbye to everyone, and let everyone come cam up on the Zoom meeting here. So
excellent.
And
thanks so much.
We are.